All right, in a prior video, we looked at functions, polynomial functions that had parameters in them, and those functions could be acting as models for some particular situation. So in this video, we're going to look at functions that have exponential functions, but also have parameters in them. So I thought would be a good examples to start with, that we have some function h of x is equal to e to the negative x plus k times x. And again, we're trying to focus on the critical points or critical numbers problem. And we're just trying to understand in this problem, how does the value of k, the value of the parameter k, how does that affect the location of critical numbers? Right? That's what we want to look at in this problem. Okay? So we know that critical numbers come down to finding the derivative of the function. The derivative of e to the negative x is negative e to the negative x according to the chain rule, and the derivative of kx is equal to k. Okay? Now if it comes down to us solving that equal to 0, okay, we could move the k to the other side as a negative sign, and we want to try to solve for x. That's the critical number problem, and that would require that we multiply both sides by a negative. Okay, we could take the logarithm of both sides, right? So we get e to the negative x is equal to k, take the natural logarithm of both sides, and that would give negative x is equal to the logarithm of k. And so x, our critical number, is negative logarithm of k. Okay. Now we can see here that there are some different scenarios that might come into play. All right. Is there a case where there's no critical point, right? And you're saying, well, here's the critical point. X is equal to the negative logarithm of k, right? So whenever you can take the logarithm is when you're going to get a critical point. But if k is a number less than 0, the logarithm of k does not exist, right? And so k is allowed to be any constant, so specifically it can come out to be a negative number, in which case the logarithm of k would not exist. Okay? If k is positive, right, then there is only one critical point, and that is x is equal to the negative logarithm of k. So, for example, that if k was equal to 1, which is a positive number, then our critical point would occur at negative logarithm of 1. Logarithm of 1 is equal to 0. So this function would have one critical point at 0, right? And whenever k is positive, there will always be one critical point, right? And then the next thing to say is, when does the function have a horizontal asymptote? Or in other words, as x gets really big, the limit as x goes to infinity, what happens to this limit? Right? Can this function ever have a horizontal asymptote? Right? Well, as x gets really big, this exponential gets smaller and smaller, it gets closer and closer to 0, but kx gets closer and closer to infinity. Right? So I'm not seeing a asymptote in this problem. I'm not seeing this get close to an actual number because the kx term is making this blow up to infinity. So, the next thing to do is to kind of look at the graph in Desmos and see how some of this is playing out. Okay, so let's look at the function h of x is equal to e to the negative x. We're familiar with this function, but now we've added on plus a constant times x term, and we want to add a slider for x. Okay, and we can kind of take a look at what this function is telling us. Okay, now again, when k was equal to 1, we had a critical number there at 0. That's, I think, what we can see right here. When k is equal to 1, we were supposed to have a critical number at 0. Okay? And the bigger k got, right? So for example, when k was equal to 2, right, our critical number was negative logarithm of k. So if you take the logarithm of 2, you get 0.69, and then the critical number moved to the left because our critical number was negative logarithm of k. So this critical number right here, where this minimum occurs, is at negative 0.69, right? And the bigger k gets, right, the bigger k gets, our critical number moves to the left. Okay, and so the graph changes a little bit. Sorry, let me move back out. Our critical number is moving to the left, and our function is looking like a local minimum. Okay, and as x gets bigger and bigger, our function stops looking like the exponential function because that term is getting closer to 0, and our function is starting to look more like a straight line, k times x. But no matter how you zoom out on that thing, our function actually never levels off to become a horizontal asymptote. Okay. Now the next thing to see is that when k was positive, we had a local minimum, right? And so we can see here that when k is 1, when k is 0, getting closer and closer to 0, we still have a local minimum, right? But now that local minimum looks like it's a positive number. And that's because when you take the logarithm of 0.2, the k value, and then put a minus sign in front of that, the critical number comes out to be 1.69. That's where this minimum occurs. But as soon as k gets to be a negative number again, a negative number, we can see that our formula said that we didn't actually get any critical values because the logarithm of a negative number was not defined. So this function just keeps decreasing and never actually turns and has a local minimum. And we can see that there are no horizontal asymptotes. If you look at this function for all these different values of k, there's no place where that function actually levels out and becomes a straight horizontal line. This function is always kind of becoming a straight line with a slope. Okay. So ends this video with our first problem analyzing the critical points for a function with exponentials in them. The next video we'll look at some problems with a couple more exponential functions.